So in the last class, I have said that mathematical expectation does not exist for all functions. So let's have a look at whether that is true or not. So let's take a case in the case of x, when x is discrete random variable. So let's have a look. In the case of discrete random variable, for example, if I take xi is equal to 2 raised to I, and the corresponding p of x is equal to 1 by 2 raised to I. Now, what is the mathematical expectation, or what is the formula for mathematical expectation when x is a discrete random variable? What is it? Yes, expectation of x is equal to nothing but summation xi p of xi. So now let's substitute these values in this equation and check whether it is the mathematical expectation exists or not. Summation 2 raised to I multiplied by 1 by 2 raised to I, which is equal to summation 1, which is equal to infinity. So it's clear from this problem that the mathematical expectation does not exist for xi in this case. Why? Because it is infinity. The answer that we get, or the right hand side, is infinity. It does not converge absolutely. So that's why in certain functions mathematical expectation does not exist, and this is one of the examples for that. Now the second example I would like to take when x is a continuous random variable. So when x is continuous, I'm going to give a function f of x is equal to 1 by pi into 1 plus x square, and the range of x is nothing but minus infinity less than or equal to x less than or equal to infinity. So again, when I use the formula for mathematical expectation for a continuous random variable, what is the formula for that? Yes, you are right. Expectation of x is equal to integral over x f of x dx, and that is equal to integral over, in this case the integral x takes the values from minus infinity to plus infinity. That means minus infinity to plus infinity, x 1 by pi into 1 plus x square dx. So it's clear from this formula that that the range of x is between minus infinity and plus infinity, and hence the function, whatever calculations we do, that right hand side won't converge. But our condition is that for the mathematical expectation, if it should exist, what was the condition? The right hand side should converge absolutely. But in this case it won't converge, and since it does not converge, what does that means? Mathematical expectation does not exist for this random variable in this particular case. Addition theorem of expectation. If x and y are two discrete random variable, then expectation of x plus y is equal to expectation of x plus expectation of y, provided all the expectations exist. All the expectation in the sense expectation of x and expectation of y, both expectations should exist. So let's have a look at how we prove this theorem. Okay, now it is said that x and y are discrete random variables. Okay, then the marginal density function of x, marginal function of x is nothing but f1 of x, and that of y is f2 of y, and the joint period of x and y is f of xy. Okay, also f1 of x is equal to summation over y f of xy, and f2 of y is equal to summation over x f of xy. Okay, now let's move on to find out what is expectation of x plus y. We have to prove that the LHS is equal to RHS. Now, expectation of x plus y is equal to expectation of x plus y. What is the formula of expectation of x when x is a discrete random variable? Just keep that formula in your mind and apply it over here. So what you get is nothing but summation over x plus y into f of xy. Now here I am going to open this brackets. I am going to expand the RHS. So when I expand the RHS, I get summation over x, summation over y, x into f of xy plus again summation over x and y, y into f of xy. Okay, which is equal to, I'm going to do some rearrangements over here. Summation over x, summation over y, f of xy plus summation over x, f of xy and summation over y. So this is clearly but nothing but what is this? Summation over y, f of xy is nothing but what is it? What is it? Yes, you are right. You know that it's given over here. What is it? f1 of x. So you can substitute that f1 of x plus summation over y and what is this? Yes, it's nothing but f2 of y. And again, what is this form? Summation over x, x into f1 of x that you have studied already. What is it? It is nothing but expectation of x plus this value is expectation of y. Hence, you get the RHS and the theorem is proved. Now let's discuss the multiplication theorem with respect to the mathematical expectation. Now, see, the expectation of product of two independent random variables is equal to the product of their expectations provided all the expectations exist. So what I have written here, it's written in the equation right below, and what is that? Expectation of xy is equal to expectation of x multiplied by expectation of y. Now we will have to prove this theorem. Okay, so let x and y be two random variables. Okay, these x and y are two random variables. They are discrete random variables. Okay, and let f1 of x and f2 of y be the marginal density function. Okay, marginal PDF. And f of xy is the joint PDF. Okay, now what is f of xy? Since x and y, it's clearly stated in the theorem that x and y are independent random variables. So since x and y are independent random variables, I would like to say that f of xy is equal to f1 of x and f1 of x into f2 of y. Okay, now let's take a look at the LHS. What is the LHS? Expectation of xy. Now expectation of xy is nothing but summation over x, y, xy and its PDF f of xy, which is equal to summation over x, summation over y. Instead of f of xy, what can I write? f1 of x multiplied by f2 of y. So xy into f1 of x multiplied by f2 of y. If I do some rearrangements over here, I can get this right hand side as summation over x, f1 of x, summation over y, f2 of y, and what is this? What is this? Yes, it is nothing but expectation of x, and what is this? It is again expectation of y. So Hence, we have proved that expectation of xy is equal to expectation of x into expectation of y. Now let's have a look at the Cauchy-Schwartz inequality in terms of mathematical expectation. Now, according to Cauchy-Schwartz inequality, in terms of mathematical expectation, it is nothing but expectation of x by the whole square is less than or equal to expectation of x square multiplied by expectation of y square. Now, here let x and y be two random variables. We have to prove this inequality. So, our first step is nothing but, as we always say, x and y are two random variables. Now here you have to consider another random variable, and that is nothing but x minus ay. So this is also a random variable. Now you have to find out the expectation of the square of this random variable, expectation of x minus ay the whole square. Now it's clear that this value or this term is always greater than or equal to 0. And why? Because the mean square of a random variable is always greater than or equal to 0. That you have studied earlier when you studied your basic statistics, right? So this is because the mean square of a random variable is always greater than or equal to 0. Now let's have a look at the LHS, that is left hand side. Now we'll try to expand this value. Okay, now let's see expectation of x minus ay the whole square. Let's expand this term. So what you get is x square minus 2xay plus y square, right? And this is greater than or equal to 0, which implies that expectation of x square minus expectation of 2xay plus expectation of y square is greater than or equal to 0, which implies expectation of x square minus, since 2 and a are constants, I'm going to take that outside. So 2a expectation of xy plus expectation of y square, which is greater than or equal to 0. As I said that a is any constant, I'm going to give it a value. A is equal to expectation of xy divided by expectation of y square. Now my next step is to substitute this a value in this equation. Let this equation be 1. So I'm going to substitute a in the equation 1. So let's have a look at what we get when we substitute a in equation 1. So after substituting a in equation 1, we get expectation of x square plus expectation of xy divided by expectation of y square the whole square multiplied by expectation of y square minus 2 into expectation of xy divided by expectation of y square multiplied by expectation of xy, and this thing is greater than or equal to 0. Now I'm going to do some I'm going to cancel expectation of y square, and we have expectation of y square here also in the denominator. So I'm going to cancel, and then I'm going to structure this equation like this, and finally I get what? Expectation of x square minus expectation of xy the whole square divided by expectation of y square is greater than or equal to 0. And from this inequality, I'm going to get expectation of x square multiplied by expectation of y square greater than or equal to expectation of xy the whole square, and hence the inequality is proved. Now we are going to find out variance in terms of expectation. Now let's see, v of x is equal to expectation of x minus expectation of x the whole square, which is equal to, I'm going to expand this right hand side. So let's see what we will get when we expand the right hand side, plus expectation of x the whole square, which is equal to, I'm going to take this expectation inside this bracket so that I get expectation of x square minus 2 into expectation of x into expectation of x. See, expectation of the mean is again the mean itself, that is expectation of x bar is equal to x bar itself. So with that I'm going to, there won't be any change over here, so I'm going to write this down as it is, expectation of x plus expectation of x the whole square. Again this is also applicable over here, which is equal to expectation of x square minus, what is this, expectation of x the whole square plus expectation of x the whole square, which is equal to expectation of x square minus 2 plus 1, what you get, minus expectation of x the whole square. So that is how you write the variance or v of x in terms of expectation.